Welcome to the lesson 32 of industrial instrumentation. This is a continuation of lesson 31. Actually, we'll consider here the dissolved oxygen sensor. We discussed basic principle of the dissolved oxygen sensors in details in the lesson 31. This particular lesson will consider the different types of electrodes, its calibration, type of membrane. These are the very important things for designing any DO2 probe, and type of type of materials which is used for making the electrode, especially the electrolytes, and what should be the suitable nature of the membrane. Also, that is also very important, because in some cases you have to sterilize the dissolved oxygen sensors when it is used in the bioreactor, or you will put in the autoclave. So, the temperature, minimum temperature there will be 120 degrees centigrade. So, in that type of situations we will discuss, we need some sort of autoclaving and with a or some sort of sterilizations. And these particular lessons we will discuss all those in details. As I told you earlier, that it is a continuation of the lesson 31. Let us look at the contents of this lesson. Lesson 32, dissolved oxygen sensor 2. Contents: construction of electrodes, how the electrodes, what is there, or what is anode, what is cathode, what type of material used for making anode and cathode, what type of electrolytes we are using, where the membrane lies. So, all these things we will discuss. Then Clark type electrodes, we will basically consider 4 different electrodes. So, that we will discuss one by one. What are the advantages, what are the disadvantages, what are the relative relative properties of these particular electrodes, that we will discuss. Then Mansi electrodes, this is all this name actually given by some inventors. So, those are most widely used for bioreactors. So, that we will discuss in this particular lesson. Mackereth electrode, then we have Barkowski and Johnson electrode. So, these are the 4 different electrodes we will discuss in this particular lesson. At the end of the lesson, the viewer will know different electrodes and their construction. Okay, 4 different electrodes, what are their construction, the instrumentation necessary, because you see that it's usually the current which we will get from the dissolved oxygens is very low. So, what type of precautions we will take, all those things we will discuss in this particular, what type of amplifier we will use, all these things will be discussed in this particular lesson. Then calibrations of electrode, because calibration is most important. So, there are we can calibrate it in 3 different conditions, either in the partial pressure, dissolved oxygen concentration. All these things will be discussed in this particular lesson. Design of electrodes. The membrane covered DO2 electrodes basically consist of a cathode, an anode, and electrolyte. It is basically, it is a probe like a pH probe. So, it has a same thing. We have a DO2 we have a cathode, we have a anode, and the electrolyte. One thing we are missing here, we are talking about, there is a membrane. Anyway, it is a part of the so electrolyte is most important, as I told you. So, there will be 3 parts, one will be cathode, one will be anode, and there will be electrolyte. Also there will be membrane. In designing DO2 probe, DO2 means dissolved oxygen concentrations, or dissolved oxygen, as you know, actually we are measuring partial pressure, that is converted into the concentrations. In designing DO2 probes, the following requirements are generally considered. What are those requirements? The calibration has to be stable over a long period. Usually, you know that in bioreactions, it takes a long time. Some of the reaction takes over several days to complete the reaction. No reactions will be less than 72 hours, some even longer. So, the stability of the calibration, that means whatever the reading it is giving, there are many problems we will find. There is a depositions on the cathode, those things are there. So, it will change the calibration. So, we have to avoid that type of change of calibrations, otherwise entire output will be wrong. So, this to be very careful. So, the stable of calibrations is more important. So, calibration has to be stable over a long period, number 1. The current output of the probe has to be sufficiently large and linear with DO2. DO2 means dissolved oxygen concentrations or partial pressures of the oxygen, whatever way you say. right? It should be linear, that is most important. Otherwise, if it is non-linear, so it's very difficult to calibrate. So it's linear is, that's I mean the basic principle or the basic desirable characteristics of any instrumentation systems or instrumentation sensors. So we will consider this thing. Then we have the effect of liquid flow on the probe performance has to be small. Okay, so if we suppose we are putting this probe on a liquid which is moving, so in that type of cases, so the liquid flow on the, because there is a permeable membrane through which liquid may come in, or the electrolyte may go out. So those things is to be cared, or this needs to be think of. The time constants of the probe should be small. This is another important thing. Time constants of the probe should be small. The temperature, that means if the response time should be very fast, that is I am talking about, the response time should be very fast, or the time constants of the probe should be, that is also desirable, because sometimes we will find it is out of our control. We will try always to make the time constants. We will see that in some considerations, if we particularly design this electrode in a way that by which I can get a fast response time. Usually, you know, the bioreactors, we are not much concerned with this thing. You will find that the most of the bioreaction cases, you will find the time constant is typically large, right? Suppose there is a reaction which is going on for 72 hours, so you will find, or 48 hours. Even if you sample the each sensor's output 10 minutes, 6 minutes, 10 minutes, that is to be considered to be quite high also, because any reactions, it takes a long time. It does not change that rapidly that you have to sample every minute. So the time response, we should not give much emphasis on this, but sometimes we need, we have to take some action. Suppose, suddenly the dissolved oxygen concentration or partial pressure of the oxygen falls, immediate action is to be taken. In that type of situation, obviously, if you have a lower time, time constants or the fast response of the sensor, that is always helpful for taking actions and all those things. Anyway, temperature compensation technique is to be incorporated in instrumentation, because as you know that if the temperature changes, so many properties of the probe will change. So that will change, because the electrolyte properties will change. So there is some sort of temperature compensations, or more precisely I should say the ambient temperature compensation should be incorporated. That is a part of instrumentations. Then we have the probe must withstand high pressure and repeated autoclaving. This is also a problem, because you know that in a bioreactors, whenever we are using the sensors, so obviously one important thing is we have to make autoclave. We have to sterilize. Autoclaving, some sort of, I should say, it's like a pressure cookers. All of you have, it's a household, like a household pressure cookers which you have seen. Usually the temperature of these pressure cookers, inside temperatures, you have to rise it. If you have to raise the temperature, suppose 120 degree centigrade something, you have to increase the inside pressure. Okay. So the probe should withstand that high pressures as well, which is obviously more than atmosphere, and high temperature. Repeated autoclaving also is, one of the desirable properties of having a good probe. In actual probe design, some of the above requirements are emphasized more than the others depending on the specific application. You cannot get all these things on a single probe design. We have to dispense of some of, we have to throw out some of the requirements, we have to take some of the requirements the most, which is more important for our particular applications. Construction methods. Clark type electrode, let us look at, as shown in figure 1, which will come after some time. That this probe is characterized by a flat disc type cathode and a pool of electrolyte in which a reference electrode, which is AgAgCl, silver chloride, is immersed, right. So that is the basic electrodes we have seen. We will show that in the figure. Although the size of the cathode, the membrane material and the electrolyte differ widely, this design is most popular in commercial DO2 probes for use in the laboratory or in the field. This is the most common sort of, these electrodes. That is the reason we have put in the position number 1, the Clark type electrode. Let us go to the details of this. This you see the figures. This is a Clark type electrode. You can see here. We have anode, AgAgCl. Cathode we have, which is made of platinum. Then you have membrane. Usually this membrane is made of Teflon. There is a O-ring, it's like this one, which is to be tightly put so that the membrane will be in contact. Membrane will be will hold in a position. and we have electrolyte throughout the medium. You see the electrolytes are here, right. So, this is our this is the two probe output, is a two wires is coming out, which is to be connected. You can see here two wires are coming out. So, through which I will show the circuit how we will measure that current, right. So, this is our basic Clark type electrode. The probe malfunction is caused by AgCl deposition on the anode surface, okay, and depositions of silver on the cathode, depositions of the silver on the cathode, and depletions of chlorine from the electrolyte or loose membrane. So, loose is to be, this membrane is to be very tight. So, that is the reason we are using a O-ring, which is will put the membrane very, because we have seen, you see here we have a membrane here, okay. Sorry. So, you have a membrane here we have seen. So, this should be tightly so that no electrolyte will come out. You can see here cathode and anode is there. So, caused by AgCl depositions on the anode surface, that means on the platinum surface, and depositions of silver on the cathode, which is a platinum, and depletion of Cl from the electrolyte or a loose membrane. These are the most important things. However, with proper cleanings of the electrodes, membrane replacement, time to time replacement of the membrane, and electrolyte replenishment and the frequent calibration, these probes can be used for a long period. So, this type of probes can be, this is a very, I should say very obvious sort of, any sensors we will use, you have to need frequent calibrations, okay. Any probe, whether it is a pH or measuring the conductivity or measuring dissolved oxygen concentration, everything we need some this type of depositions will be there. We have seen the polarizations, all those things are there. So, it is to be repeated cleaning, then replacement of the electrolytes, or it is supplied from some a reservoir, permanent reservoir. So, that type of thing obviously will make the, and frequent calibrations will make make the sensors for a longer use, okay, over the period of time. With a 25 micron Teflon membrane, 95% response time of 15 to 20 seconds is usually obtained, right. Response time means that it is a within 15 to 20 seconds. If you consider as a step input, suddenly that suppose a probe is inserted or there is a change in the concentrations of the dissolved oxygen or partial pressure of oxygen. So, if we use a 25 micron Teflon, so 95% response time is usually obtained, right, of 15 to 20 seconds is usually obtained. But these sensors show a hysteresis, the response to an increased oxygen concentration is faster than that to a decreased oxygen concentration. Okay, step change, it basically response time varies depending on the direction of the step change in oxygen concentration. Suppose I had, because it is very unusual though, its oxygen concentrations or oxygen partially does not change very rapidly, but suppose there is a change, suppose. So, that is what I am saying, there is some sort of a hysteresis in the systems, but the sensor shows a hysteresis, that means that the response to increased oxygen concentrations will be different than that when we are decreasing the concentration. This phenomena is caused by the electrolyte acting as a reservoir of dissolved oxygen or the accumulations and slow decompositions of hydrogen peroxide in the vicinity of the cathode. Mansi electrode. The galvanic probe originally designed by the Mansi is shown in figure 2. The major difference from the Clark electrode is the elimination of the electrolyte chamber. Instead, a thin film of electrolyte is placed between the cathode and the membrane, and it will eliminate the hysteresis. The hysteresis is the problem, that means increased concentrations and decreased concentrations, it will be giving a problem. So, that type of problem can be eliminated in the Mansi electrode, right. So, this is our Mansi electrodes. We can see here plastic casting is there, the membrane is there, an AG cathode, we have a PB lead anode and plastic collar. Okay, this you can see here. Due to relatively large chamber, 0.6 centimeter cathode employed, a microammeter could be directly connected to the probe. Okay, we do not need further amplification. An improved probe stability was reported compared with the earlier polarographic probes, but the useful probe life may be somewhat restricted because the available surface area of the anode is relatively small. So, this is another problem. The anode surface is gradually oxidized with the use until the probe ceases to function. Okay. So, it will be oxidized and until the probe ceases to function. Mackereth electrode, it looks like this. It was noted that the Clark electrode and the Mans electrode lacked long term stability, as I told you, because the depositions and all those things. So, because in the case of Clark electrode we have to clean it, all those things are there, whereas here there is a deposition in the case of Mans electrode. So, this type of thing will be not there in the case of Mackereth electrode. It was noted that the Clark electrode and the Mans electrode lacked long term stability and produce small currents of the order of microampere. We have seen that the current is quite small. Mackereth probe eliminate all these problems. Here a perforated silver tubing was used as a cathode and the massive shot of porous lead was used as the anode. Okay, figure 3. Porous PV, lead is the anode, and this is electrolyte. You can see we have a O-ring and perforated tubing, cathode. Okay, so, this is our Mackereth electrode. You can see here we have a O-ring and membrane is there. The current output was much higher than those of the other probes, so that an ordinary current meter can be directly connected to the probe without amplification. This is very important because obviously any reading you will find it is corrupted with noise. So, that if the current output is large, so all these problems, signals and noise ratios will be quite good. So, we do not need any further amplification. The sensitivity was stable over many months of continuous operation. This is again a very important thing in the case of electrode design. With a 25 micron Teflon membrane, this probe gave a 90% of its steady state value in 1 minute. Okay. So, it is quite fast, not that fast compared to the Clark or electrode, but as I told you that response time fast is not very stringent requirement or a very rigid requirement for bioreaction. So, in that type of application this probe can be nicely used. Most important thing, it can be used over a longer period without any recalibrations or recleaning. Because of its long term stability, this probe has been used for monitoring the dissolved oxygen concentration in continuous cultivation, which lasts several weeks. In some cases I said 72 hours, in some cases it is can be continue over a week. So, in that type of situation this electrode is very much suitable, though the response time is very is quite bad, I should say, but it does not matter because I will not sample, I will not measure every minutes, I may measure every hour, because if the reaction going on for several weeks, obviously just reading in half an hour of the dissolved oxygen concentration will suffice. When vertically inserted in a air sparged cylinder vessel, the Mackereth probe exhibited a response free from any effects of air bubbles ascending through the vessel, which is very obvious in many situations we will find, whereas other probes, because this type of situation will arise in the air column, bubble column bioreactors. So, bubble column, you will know that a basic principle is something like this, that it is like this. I have so dissolved oxygens are because instead of, suppose I have a star tank reactors here. So, it is rotating and like oxygens are getting dissolved. In the case of bubble column reactors, what will happen? What will happen that I have a vessels and I am purging oxygen through this one. So, bubble will go out like this one, it will go to the air bubble will go. So, it will purge along this one. So, this type of may cause problem in other type of dissolved oxygen probe, but that will not make a problem in this probe. Let us go back. When vertically inserted in an air sparged cylinder vessel, the Mackereth probe exhibited response free from any effects of air bubbles, because the function of the air bubbles to increase the dissolved oxygen concentrations or partial pressure of oxygens in the bulk medium of the liquid, where actually my reaction takes place, right. Where the other probes in this case, so that is the most important thing which you should consider. That problem does not arise, if you use a Mackereth electrode. So, the Mackereth probe exhibited response free from any effects of the air bubbles ascending through the vessel, whereas other probes with cathodes at the tip showed interference due to bubbles touching the cathode. So, this is again problem in other. Since the cathode area is relatively large, a vigorous agitations of the liquid is required for reliable operations, okay, because since the cathode area is large. So, obviously, it should average. So, the vigorous agitations of the liquid is required for reliable operations, and the oxygen consumption by the probe must be considered using the probe for measuring oxygen in a small liquid volume. So, it is obviously if you use a CSTR continuous start tank reactor, obviously the liquid will be vigorous. Only problem, this condition will not be satisfied if you make a very gentle rotations of the blades, so that the in very sensitive culture like animal cell and all these things. So, this question arises. Otherwise, for the most of the conditions like the reactions whether we are using CSTR continuous start tank reactors. So, this type of problem does not arise. So, this type of condition will always will be there, because it is rotating at a high speed. So, obviously, there is vigorous agitations of the bulk medium of the liquid. The probe may not be suitable for a viscous medium if the viscous is the liquid. This is another problem, because you see the bioreaction, the viscosity does not remain same. At the initial stage when the reaction starts, the viscosity will be less. As the reaction going on, for an example, very trivial things I am talking about the yeast growth, you will find that as the reaction goes by, at the end of the day you will find that the liquid becomes very much viscous. So, need for a tubing membrane makes it difficult to fabricate the probe in the laboratory. This is another problem, which is like in the Clark electrodes, it is very simple to make. Brokowski and Johnson electrode. The original design was by Johnson, but it was improved later by Brokowski for a longer life and better stability. As shown in figure 4, the cathode is made from a silver spiral, and a flattened lead wires forms the anode. A low pH acetate buffer is used as an electrolyte to prevent interference by the dissolved carbon dioxide. This probe has been used widely in the biochemical engineering applications. You see here we have a glass tubing, anode is there, which is helix. Then we have electrolyte, we have a glass wool there, a cathode which is silver spiral, sorry. And we have a membrane, silicon tubing is there. So, this is our glass tubing, and two wires are coming out. The probe can be withstand repeated steam sterilization and is capable of operating for several months as a linear response. With a 50 micron Teflon membrane, 90% of steady state value is reached in 1 minute. It is almost same as the previous electrode, Mackereth electrode. A vigorous agitations of the liquid at least 60 centimeter per second for water. Okay, velocity, rotational velocity if you take is required for reliable measurement. The probe is not suitable for viscous liquid unless thicker membrane is used, same as the previous electrode. Oxygen microelectrodes. The major consideration with these probes are a high spatial resolution and a fast response time, because in some conditions we may need a fast response. So, in that type of cases 1 minute or even 20 seconds is might not be very desirable properties. We have to reduce that. So, that we can do in this type of oxygen microelectrode. As its name implies, it is a very small in size. High spatial resolutions and a fast response time. When the cathode diameter becomes less than 1 micrometer, even a bare metal cathode, okay, which is figure 5a, becomes insensitive to liquid flow and measures local oxygen tensions or oxygen concentration. It is almost the same thing. You can see here. So, 5ABC, all these are, this is a bare, this is glass insulation, this is a cathode, this is a membrane, and this is like this one, okay. Recessed, membrane covered and recessed, three difference we have shown. The probe performance is improved by covering the cathode with a membrane, okay. Obviously, if I cover my membrane, so it will be responsibly slower, and by extending the insulation such that shown in figure 5c, diffusion gradient is confined inside the recess. A thick platinum wire is first etched in an electrolyte solution to a fine point of 0.2 to 1 micrometer diameter, then insulated with a thin layer of glass, right. I will repeat, a thick platinum wire is first etched in an electrolyte solution to a fine point of 0.2 to 1 micrometer diameter and then insulated with a thin layer of glass. The membrane is applied by a deep coating. Polystyrene is most popular, but other materials have been also used. Although the capillarity of the local oxygen measurements is attractive, several problems exist with these microprobes: extremely fragile, unstable, useful probe life is short, moreover the instrumentation is difficult, repeatability of the sensor is poor, each and every sensor is to be calibrated separately. So, all these problems are there. Now, electrode metals, what type of metals we will use in the electrodes? We will cover one by one: membrane, type of electrolytes we are using, all these things, and finally some instrumentation. The oxygen reduction at pre-oxidized metal electrode is a pH dependent, whereas for pre-reduced metal electrodes the reduction was pH independent. For polarographic probes, platinum, gold, silver or rhodium have been used as a cathode, and silver chloride, silver or dioxide is Ag2O. Please note, it is not Ag2O, it is Ag2 will be in subscript. So, it is like this. So, it will be 2O, sorry. So, I can or calomel as a reference electrode is used. Gold is generally preferred to platinum as the cathode material because it is less susceptible to poisoning by noxious gases, notably H2S, hydrogen sulfide, and the reaction at the cathode surface is less complicated and the surface aging is less pronounced. However, gold may not convenient for application in steam sterilizable probes and the macro electrode, since gold and glass cannot be fused together. So, it is a larger type of electrodes. If I want to make steam sterilizable, that is not very suitable for this type of purposes. Gold plating method has been used in making the micro electrodes to circumvent these problems. So, that if the macro electrode is not possible, but micro electrode it is possible. The reference electrode has to maintain a stable reference voltage for a good performance of the polarographic probe. Also, it has to have a large surface area to avoid polarizations. So, the surface area should be large. Silver chloride is normally used as a reference electrode. However, silver dioxide is preferred because it gave better stability for their probe. The aging effect of the polarographic probes, such as the change in calibrations or unstable probe sensitivity, is attributed to the depositions of silver ions on platinum and the oxidations of the catalytic surface or an excessive depositions of silver chloride on the reference electrode. The cathode surface can be mechanically cleaned with soft scouring powders. So, if you regularly clean it with cleaning powders and a wet leather or by toothpaste. So, excessive silver chloride deposits can be removed by washing with ammonium hydroxide, 15% ammonium hydroxide is possible. These I told you from the very beginning, regular cleaning of the electrodes. For galvanic probes, the silver as the cathode and the lead as the anode are most common, but silver aluminum, platinum lead, gold zinc, gold lead pairs have also been used. Although the galvanic probes suffered less from poisoning and survive autoclaving with greater reliability, the probe life is limited by the available surface area of the anode due to gradual oxidations of the anode surface. This is again problem. The useful lifetime of given probe depends on the current drain, just like an electric battery. In other words, a probe can be used much longer when it is used for monitoring low rather than the high oxygen concentration. This is not in our hand. So, it varies. Suppose in a reactions, because in many reactions in bioprocess we have seen that you see the Many concentration we cannot measure online. Suppose the substrate concentration, cell concentrations we cannot measure. Only the DO2 we can measure, and that will give you the, suppose when the DO2 is initially is when the reaction starts, we find that the DO2 is not growing that fast. That means the whatever the DO2 we are supplying, that is consumed by the cells. At the end of the reactions, after several hours or might be several days, we will find that no more oxygens are getting consumed, so DO2 concentration is increased, but coming to a steady state. That means you can see that whatever oxygens we are supplying, it is getting consumed, and after that if it is increased further, so DO2 again will find that it will indicate that the cell reaction is complete. It is time to take out the cell from our, or take out the product. So DO2 concentration measurement is very important, right? So and it's varying, so that it's not in our hand, but in some condition where we have just a monitor, not much of control, that means what is the value of the DO2 in a, what are the safe level of DO2 in the oxygen. Suppose in the marine animals will need the measure the DO2 concentrations there. So in that type of situations we can say that we can either low monitoring or high monitoring, okay, but it is not in our hand. Electrolytes. Since the electrode reactions occurs in the electrolyte solution, the composition, pH and the volume of the electrolytes are directly related to the probe stability. For polarographic probes, the electrolyte takes part in the reaction, so a refill of electrolyte is necessary in the regular intervals. Okay, this is a very important thing. It is very difficult, so that what we have to do, we have to use a reservoir. We will discuss in the next slide. In general, pH of the electrolyte does not affect oxygen reduction on a clean metal surface, but an adverse effect was observed for an oxidized metal cathode. The solubility of the electrode metals in the electrolyte solution has to be low for probe stability. Sometimes the polarization voltage may change depending on the electrolyte concentration. In this case, the change in the electrolyte concentration due to evaporation or diffusion of water through the membrane affects probe stability, because any liquid you will find when you make the reactions, mostly it is in water. So water may diffuse through the membrane, okay. So that will again change the properties of the electrolyte. Various electrolyte solution used, by different investigators. For polarographic probes, potassium chloride is the most common electrolyte, which gives a constant calibration well over 48 hours, which is quite okay for many of the applications. For galvanic probes, preferred potassium hydroxide than the potassium chloride, because potassium chloride gave a high residual current and it did not maintain a clean anode surface. The solubility of silver is reported to be high in KCl solution. It was found that only KCl and K2HPO4 gave a linear response up to a high oxygen concentrations and also were steam sterilizable, right. So, again the steam sterilizable is a good property, and also autoclaving is a good property of the system. That is also always you have to think about, because the contamination is a great problem in all the reactions you will find, especially when you are using the bioreactors. If you are using the field, that does not matter, because many reaction does not allow a little contamination. That is to be, you have to think that in mind. A rather serious problem with the electrolyte is the loss of solvent through the membrane by diffusions or evaporation. Several methods have been used to minimize this effect. One method, by having a large electrolyte reservoir, as I told you, which can effectively supply solvent to the electrolyte film where the solvent loss occurs. In this case, the path between the reservoir and the electrolyte film has to be as long as possible to minimize the residual current. Another method is to have electrolyte in the form of a gel or paste, okay. And added advantage is that the residual current becomes smaller, because the oxygen permeability is normally lower in more viscous medium. Recent development has been in the use of a solid electrolyte instead of the conventional liquid form. So, this all will eliminate the previous problems which we have discussed. Membrane. An ideal membrane for use in DO2 probes must have a relatively low oxygen permeability, high oxygen diffusivity, The permeability has to be low to ensure the membrane control of the oxygen diffusion, whereas a high diffusivity gives a fast probe response. Okay, so you have to make a compromise. The membrane has to be mechanically strong and chemically inert, right? That means mechanically strong means it should withstand the high pressure. It should in a position to withstand the high temperature, at least 120 degrees centigrade, little more than 1 atmosphere. It is to be because if you do for autoclaving, so this high temperature, high pressure conditions are to be satisfied. Since the current output is directly related to the thickness and the oxygen permeability of the membrane, the probe sensitivity is directly affected by the change in the membrane properties. Membrane swelling or change in the apparent oxide permeability results in the change of probe sensitivity. Sometimes membrane swells, okay, if it lies over a long time in a liquid, so that will change the apparent oxygen. This is not a problem, we have to recalibrate or you have to change the membrane, that is it, there is no other solution. Other important factors are CO2 permeability and water permeability. The water permeability of the membrane has to be low to prevent loss of water from the electrolyte solution, which causes an increase in electrolyte concentrations and early failure of the probe. Low CO2 permeability of the membrane is also desirable for probes to be used in aerobic cultures and in blood. Okay, sometimes the measurements of oxygen concentrations in blood is also important. Now the material, what are the different materials used for the making the membrane? I will say the Teflon is the most widely used material for making the membrane. Teflon, polyethylene, polypropylene have been most popular as the membrane material, but silicon, polystyrene, mylar have also been used. But still I should say that Teflon is the most widely used membrane for making DO2 probe. The polypropylene is better than the Teflon in several aspects. It has a lower oxygen permeability, a lower carbon dioxide permeability, and yet a higher oxygen diffusivity. However, Teflon seems to be more popular in steam sterilizable probes due to the higher heat resistance that I told you earlier. So this is a property which it must have. An added advantage of the Teflon is its extremely low water permeability. Okay, so this is another advantage of the Teflon. Polystyrene is popular for micro probes because it sticks well on the glass insulation and has a relatively low oxygen permeability. Polystyrenes and polyethylene are not suitable for the steam sterilizable probes because of low heat resistance. So the problem is there. On one side is that a low oxygen permeability, and other side it has a low heat resistance. Instrumentation, let us look at. Unless the current output is very large, some sort of current amplification is required for DO2 probes. Okay, so we know various types of current amplification. That signal conditions we can do, it is improved a lot, so that is not a problem. Operational amplifier which provide multi-range amplifications and zero current suppressions are normally used for this purpose. Often existing current amplifiers, voltmeters or strip chart recorders are directly connected to DO2 probes. Obviously, one thing we have may not mentioned that you see any DO2 probe must be any DO2 probes must be appended by a obviously by followed, I should say, followed by a current transmitter, because the current amount of current you will get there directly from the probe is not sufficient to be transmitted, it is not sufficient. So we have to use some current transmitter so that it will go to the computer, right. We can monitor there itself, whatever the current we will get, that is sufficient for monitoring, but for control purpose if I have to send to the computers, I have to use some current transmitter there itself. So any probe must be associated with a followed by a current transmitter. For polarographic probes, a bias voltage of 0.6 to 8 volt depending on the type of electrodes has to be externally applied. That we have seen, always we need a bias voltage which usually lies between 0.6 to 0.8 volt. A mercury battery is preferred as a voltage source because the voltage discharge characteristics are superior to other batteries. For galvanic probes, usually a resistor is connected in series with the probe and the voltage drop across the resistor is monitored with a voltmeter or a potentiometric recorder. Now general design considerations, if I look at, One of the important considerations in DO2 probe design is to minimize the residual current, which is defined as a current output of the probe at 0 oxygen level. That means, when there is no 0 oxygen level, but you may immediately ask the question, how will you know that is a 0 oxygen concentrations in the bulk liquid is 0? We will show that thing, how you can make it 0. Sometimes it is called the background, dark or 0 or offset current. I should say the background current, I should say the dark current, that is more appropriate name. There are 4 major sources which contribute to the residual current: electrochemically active impurities in the electrolyte, electrical leakage, incorrect polarization voltage, back diffusions of oxygen. The effect of reducible or oxidizable impurities in the electrolyte is normally of short term duration, because they are scavenged by the cathode at the early stage of operation. Electrical leakage between the anode and the cathode through the insulating material is not normally significant for leakage for large cathode, but becomes a problem for small cathodes. For example, the insulation requirement of the microelectrode has to be better than 10 to the power 7 into 10 to the power 10 ohm. That means you can see that it is around coming around 70 gig ohm, and have a residual current of less than 10 to the power 11 ampere. That means 0.1 picoampere. So, it is quite small. This is why glass is used as the insulating material for small cathodes. It will give you very less residual current. Epoxy resins, unless specially selected for their water resistance, often absorb water and increase current by forming an external conducting path between the cathode and the anode. This is again problem, because usually you use resins to hold this different cathode anode with the systems. The correct choice and the stability of the polarizing voltage is important for stable performance of the probe. Now, figure 6, next figure, shows the 3 polarographic curves, which is called polarogram also. If the polarizing voltage is chosen between the points marked B and C and maintained in this region, the probe current will depend only on the oxygen concentration. Let us look at. Okay, you see here, if it is between B and C, if it is between B and C, okay, it is depends only on the B and C, so depends on the oxygen concentration. So, you are talking about the partial pressures of this, right. However, when the polarizing voltage is larger than the indicated by the point D, there will be residual current due to electrochemical reduction of water. If the polarizing voltage is less than that marked A, then the calibration of the current versus oxygen concentration will become nonlinear. Again, it is nonlinear region. So, if you come to the plateau region only, so that is our desire. So, that is the reason we have marked between B and C. So, it is totally because it will remain in the plateau region. So, it depends only on the concentrations of the oxygens or the partial pressure of oxygen. Since the shape of the polarographic curve changes depending on the electrode metal, the electrolytic concentrations and the size of the cathode, the optimum polarizing voltage has to be selected for each probe separately. In general, the large cathodes have wide and well developed plateaus in their polarogram, whereas small cathodes have narrow and often very poorly defined plateaus. Okay. The fourth contributor to the residual current, namely back diffusion of the oxygen from the internal electrolyte, is most pronounced for the small cathodes. Mechanical designs which favor increased path length between the cathode and the electrolyte reservoir, as well as decreasing the thickness of the electrolyte film between the membrane and the cathode, minimize the effect. Mechanically well designed probes with the above consideration in mind have very low residual current and are capable of measuring dissolved oxygen down to parts per billion, which is called ppb. Instead of part per million, we are calling it part per billion range. Galvanic probes have been preferred in the bioreactor applications, but the disadvantage is the expendable nature of the anode, because it is bioreactor, you have to make autoclaving, all those things. That is the reason galvanic electrodes is most preferred. Currently available designs of the steam sterilizable galvanic probe could be improved considerably by further decreasing the cathode area, increasing the anode area, and increasing the path between the electrolyte reservoirs and the cathode. This is the last one, is most difficult one. A well designed polarographic probe was shown to withstand repeated steam sterilizations with a high reliability. Now, operations of the electrodes, let us look at. Calibration, this is most important thing. DO2 probes can be calibrated in three ways: percentage saturations, then partial pressures of oxygen, and actual concentration. Okay. Since the reliability of measurements depends on the calibration, it is vital that the calibration done as accurate as possible, right. So, the calibration is to be, we will show the some equations by which we can make the calibrations. In all calibrations, good temperature controlled, that means 0.1 degree centigrade plus minus 0.1 of the test medium is required, because the probe sensitivity changes substantially with temperature, right. So, some sort of, I mean, in the instrumentation we should take care of this temperature compensation. Nowadays in the computers we can do this, I mean, very nicely, so that the output voltage which is coming out of the computer can be taken care of all these temperature compensations or ambient temperature compensation, if we can't do in the probe itself. Okay, that is not a problem. Calibration based on percentage saturation. Gas phase calibration is rapid and convenient. The probe output current in nitrogen is set at 0% saturation, while that in the air is set at 100%. Oxygen can be used instead of air. This method is simple but recommended only for a rough calibrations. Okay. A solution with zero oxygen content can be prepared either by stripping oxygen with a nitrogen or by using chemicals such as sodium sulphide or sodium dithionite, because by this all the oxygens will go out. These chemicals react rapidly with the dissolved oxygen to provide anaerobic conditions. Additions of 2 volumes of saturated sodium sulphite to 100 volumes of liquid is sufficient for oxygen removal. Okay, so the liquid now is totally oxygen free. So, I can make my calibrations that for my zero oxygen concentrations, what is my output, which is supposed to be 0. If it is not, that is it is offset current or dark current. Calibration based on partial pressure. DO2 probes can now known to measure the activity of the equivalent partial pressure of the reserve oxygen, but not the actual concentrations. We actually calibrate in terms of actual concentration, but actually it is measuring the partial pressure. The calibration based on percentage saturation can be directly converted to partial pressures when the barometric pressure is known, right. When the water is equilibrated with the air at temperature T, the partial pressure of oxygen, which is written as PO2, is expressed as a following equations, which is PO2 equal to PB minus PH2O multiplied by constant 0.2095. What are the legends? Let us look at. Where PB is the temperature corrected barometric pressure, PH2 is the vapor pressure of water at a given temperature, and 0.2095 is the fraction of oxygen in atmospheric air. Calibration based on concentration. The calibration based on partial pressures can be converted to concentrations, as I told you, if the solubility of the oxygen in the liquid is known. If we know that thing, how can I write? The solubility is often expressed as the Bunsen coefficient A, which is defined as the milliliter of O2 absorbed, milliliter of oxygen absorbed by 1 milliliter of solvent at 0 degree centigrade and 1 atmospheric pressure of O2, right. This is my expressions. A equal to Bunsen coefficient equal to Vg 273.15 upon Vs by T. where Vg, Vs and T are volumes of the gas absorbed and the volume of the absorbing solvent and absolute temperature respectively. For a sparingly soluble gas such as oxygen, which is very difficult to dissolve in the bulk medium, the pressure can be converted to the concentrations by using Henry's law, which is given by C equal to P naught by H, okay, where H is the Henry's laws constant and the conversions of A to H is as follows: is H equal to 22.4.14 at 760 millimeter of Hg upon 100 A. Plus, please note there are some precautions you have to take, so that I will discuss now. Those are like this. If the probes are dead, you know that this can be rejuvenated by dissolving away the oxide layer on the anode surface with the 20% of CH3COH or 20% of HCl. It's a very standard. That means if you have a, I mean, it's some sort of, it's not reacting. So clean it, the anode surface, clean the oxide layer. The anode surface should be clean with the 20% HCl, which is easily available in the laboratory. Now you see the electrode containing electrolyte. When the chloride containing electrolyte is used, the chloride ion concentration will fall as it is consumed by the anode reactions and will be replaced by the hydroxyl ion and generated by the oxygen reductions at the cathode, right. Now another important thing is, you see that the current here is very extremely small. We have seen that this current is coming around order of 10 to the power minus 10, 10 to the power minus 11 ampere. So almost like I should say 10 to the power I mean 0.1 picoampere, which is extremely small, this type of small current, right. Now, so special amplifier is required. This amplifier will not do alone, because there is, it will introduce a lot of noise. So the common mode noise, I mean we have to use some differential technique by which we can I mean eliminate this type of problem, because amount of current, there is some inherent noise in the systems, you will find thermal noise, because so that type of things, because and when we will transmit the signal over the, even the probe length, whatever the small, when it is going to the meter itself, we will find it has some length, however small it may be, because you cannot immediately you cannot connect a transmitter just over a probe itself. A certain amount of length is to be, I mean you have to, certain amount of length of the wire is to be connected. So that wire also will give some noise. So that type of things can be eliminated if you use a instrumentation amplifier at the input of this current transmitter, so that the common mode noise will go away. So the only differential mode signal will be amplified. So this thing is to be I mean you have to keep in mind. So this, I mean these are the most important thing we should think while using the DO2 sensors, but there are some precautions you have to say depending on the what are the requirements. Accordingly we will choose among the force, I mean electrodes, we will choose one, right. So with this I come to the end of this lesson 32 of industrial instrumentation. Welcome to the lesson 33 of industrial instrumentation. In this particular lesson, we will study the flapper nozzle, or rather flapper nozzle system. Flapper nozzle is a very important item in most of the pneumatic systems or pneumatic based instrumentation, because as you know that even though we are many sensors and all those things are converted to the electronic domain, but still in some cases we need this pneumatic system for the safety reason as well as for the large controlling the large control valve and all those things. And especially in the petrochemical industries or hydrocarbon industries, where the electronic systems or electrical system is forbidden to use, because there is a voltage rating which should be not it should not be above 45 volt. In that system also we need this flapper nozzle system. Now flapper nozzle system, the advantage is that you see that it has a it can be used as a displacement sensor, it can be used as a differential pressure transmitter and so on. We will discuss all these things in details. Let us look at the content. introductions, then we will go to the principle of operation, then we will go to displacement measurements and displacement sensors. Rather, we will see there how the flapper nozzles can be utilized to make the displacement sensor. We have a reverse acting pneumatic relay, because you will see that to make the keep this pneumatic sensor, flapper nozzle systems in a linear region, we will find that we should make the movement of the flapper very small. So, to do that thing we need some pneumatic relay. So, we will discuss this in details, which is called reverse acting pneumatic relay. Then we will also see the current to pressure converter or I to P converter using the flapper nozzle systems, how we can make I to P converter, because in many in the process always we need to I to P converters. Many cases we will find that whether the 4 to 20 milliampere of current we have to convert to 3 to 15 psi of pressure. So, in that type of situations we need this I to P converter. Then differential pressure transmitter, this also we will discuss in details, because differential pressure transmitter, as we know that we need it in many process, and though we have now electronic system, but still this pneumatic differential pressure transmitter is still used in many process industries, right, because as we have studied during the flow meter that in the flow measurements the flow is calibrated in terms of pressure, right, differential pressure that is to be transmitted. We can transmit 4 to 20 milliampere, but we can transmit to directly 3 to 15 psi pressure also. So, we discuss this thing how we can make with a flapper nozzle system a differential pressure transmitter. Basic introduction, you can see here two pressures, P1 sorry this P1 and P2 is coming here from the process, right, which is coming further from the flow. So, these actually from this I am getting a supply pressure, which is a function P0 is a function of K P1 minus P2, because always in the flow measurements we have seen that all differential pressure based flow meters. So, this type of output pressure, this will be this P1 minus P2 or PO will be calibrated in terms of flow. So, that is we can use a total pneumatic systems. We can see this, you see there is another this is a feedback bellows we have used. This is a bellows, please note, feedback bellows we have used. To block diagram, this if I draw the block diagram, it looks like this one. So, all the significance is P1 and P2 the output pressures, and the output pressure is coming here, two pressures from the upstream and downstream is coming here, which is combined. So, we are giving the relation like this one. Say AB1 AB2 the area of the bellows, KB the bellow linkage compliance, K in the flapper nozzle again, and in the above circuit P1 is always greater than P2, then the upper bellow exerts more forces than the lower one, always it will be greater because upstream flow is higher. Then thus the flapper moves away from the nozzle and the pressure inside the tube A falls. The feedback bellow cannot hold the flapper in such a position and brings it down. So, the output rest pressure will come P naught equal to AB1 by AB2, I1 by I2, P1 minus P2, right. So, this actually will give you the direct, this you see the output pressure is again the function of P1 minus P2, which is actually calibrated in terms of the flow. So, with this I come to the end of the flapper nozzle system.